Welcome to our deep dive into A Brief History of Time by Stephen Hawking.
Oh, a classic.
It really is.
Yeah.
This book is a landmark achievement, and I'm excited to explore its key insights with you.
It truly is a landmark. I mean, think about it. 207 weeks on the London Sunday Times bestseller list.
Wow.
That's not just a bestseller,
Holy
it's a
shit.
cultural phenomenon.
Exactly. And we're talking about a book on some pretty complex physics here.
Yeah.
It sold roughly one copy for every 750 people on Earth,
Really?
according to Hawking himself.
Wow.
Clearly, it struck a chord, tapping into our shared human desire to understand where we come from and why the universe is the way it is.
Hawking had this remarkable ability to tackle these big questions
He did.
in a way that was both intellectually rigorous and engaging.
Yes.
He didn't shy away from the complexity,
Right.
but he also made it accessible, even injecting humor where you'd least expect it.
Right, like that story he tells about the scientist giving a lecture on astronomy.
Oh, yeah.
And there's this little old lady in the back who insists.
That the Earth rests on a giant turtle all the way down.
All the way down.
It's a charming way to illustrate how our understanding of the universe has evolved, moving away from common sense assumptions and towards evidence-based models.
It's such a perfect anecdote, and it highlights how we've gone from Ptolemy's Earth-centered model, which, let's face it, had some holes you could drive a planet through, literally to Copernicus's revolutionary sun-centered model.
What's fascinating about Copernicus is that he initially circulated his model anonymously.
Really?
Can you imagine the intellectual courage it took to challenge the prevailing worldview,
Wow.
potentially facing backlash from the church?
Absolutely, but that's what makes scientific progress so thrilling.
It is.
It's about pushing the boundaries of knowledge,
Yeah.
even when it's uncomfortable.
Right.
And then Galileo comes along with his telescope, observing Jupiter's moons.
Yes.
Providing even more evidence against the Earth-centric view.
And then Kepler refines the model further, with elliptical orbits finally reconciling predictions with actual observations.
Nice.
Each of these steps represents a victory for the scientific method.
It's like peeling back layers of an onion, revealing a more profound truth with every discovery.
Absolutely.
And this journey of discovery leads us straight to Einstein's revolutionary theories,
Yes.
which form the bedrock of modern physics.
Einstein's work really shakes things up. A Brief History of Time delves into the two pillars of modern physics,
Okay.
general relativity and quantum mechanics.
And immediately Hawking highlights the central challenge.
Oh, yeah.
These two incredibly successful theories are fundamentally incompatible.
Right.
It's like having two pieces of a puzzle that should fit together but just don't.
Exactly. It's one of the biggest mysteries in physics, and the search for a unifying theory continues to this day.
Wow.
But before we get ahead of ourselves,
Yeah.
A Brief History of Time takes us on a fascinating detour through special relativity.
And that's where things start to get really mind-bending. The idea that there's no absolute standard of rest, that your motion is always relative to the observer.
Yeah.
It's counterintuitive, to say the least.
The ping pong on a train analogy is a great way to illustrate this.
Okay.
Imagine you're playing ping pong on a moving train.
Okay.
To you, the ball is moving back and forth normally,
Right.
but to someone standing on the platform, the ball's motion is much more complex.
Right. It's all about your frame of reference.
It is.
And then there's the mind-blowing concept that the speed of light is constant for all observers,
Yeah.
regardless of their relative motion.
Yes.
This leads to some truly wild implications.
It challenges our intuitive notions of space and time.
It does.
To accommodate this constant speed of light, we have to introduce the concept of space-time, the merging of space and time into a four-dimensional fabric.
4 dimensions.
Yeah.
You're losing me.
Okay, think of it this way.
Yeah?
Imagine a flat sheet representing our familiar three-dimensional space.
Okay.
Now place an object on that sheet. What happens?
The sheet dips, creating a curve around the object.
Exactly. That's a simplified way to visualize how mass warps space-time.
Okay.
And that warping is what we experience as gravity.
So gravity isn't a force pulling us down,
Nope.
but a consequence of this curvature in space-time.
That's it.
My brain hurts, but in a good way.
It's mind-bending.
And there's actual observational evidence for this.
Yes, during eclipses, we can observe light from distant stars bending around the sun.
Oh, wow.
That's because the sun's mass warps the space-time around it,
Ah,
causing the light to follow a curved path.
that's incredible. And, you know, I have to say, Hawking's ability to explain these complex ideas is simply remarkable.
He was a brilliant communicator.
He makes you feel like you're right there with him, exploring the universe's deepest secret.
Yeah, absolutely.
It's really quite something.
Yeah.
Welcome back to our deep dive into Stephen Hawking's A Brief History of Time.
Yes.
We're picking up where we left off,
right,
having just scratched the surface of Einstein's revolutionary theories of relativity. And now we're going to zoom out and explore the grandest stage of all, the expanding universe.
The expanding universe.
It's amazing how Hawking seamlessly connects these seemingly disparate ideas.
I know, it's great.
From the curvature of space-time to the vastness of the cosmos.
Yeah.
It's all part of the same grand narrative.
It is.
It's really cool.
Absolutely. A Brief History of Time takes us on this incredible journey through scientific discovery, showing how each breakthrough builds upon the last. So we've established that space-time can be warped.
Right.
But it turns out it can also stretch.
Hold on, stretch you mean like a rubber band?
Well, sort of. Imagine you have a balloon with dots drawn on it.
Okay.
As you inflate the balloon, the dots move further apart, right?
Yeah, I see where you're going with this.
That's analogous to what's happening in our universe.
So the universe is like a balloon?
In a way, yes, space itself is expanding, carrying galaxies along for the ride, and we know this because of something called redshift.
Redshift, that sounds familiar.
Yeah.
Doesn't it have something to do with the Doppler effect?
Exactly, you're sharp. Just like the sound of a siren drops in pitch as it moves away from us, light from distant galaxies gets stretched as they move away, shifting towards the red end of the spectrum. That's redshift.
So the further away a galaxy is, the faster it's moving away from us, and the more redshifted its light appears.
That's the gist of it, and this observation led to a truly revolutionary idea, the Big Bang.
The Big Bang.
If everything is moving apart, it stands to reason that at some point in the distant past, everything must have been incredibly close together.
So the Big Bang wasn't an explosion in space, but rather the expansion of space itself.
That's a common misconception, and Hawking does a great job of clarifying it. The Big Bang wasn't an explosion that happened somewhere in space. It was the beginning of space and time itself.
Wow.
A point of unimaginable density and heat from which everything expanded outwards.
It's mind-boggling to think about all of this vastness, everything we see around us.
No, it's incredible.
All originated from a single point.
It's truly awe-inspiring. Of course, there were alternative theories like the steady-state theory, which tried to avoid the idea of a beginning, but the evidence eventually stacked up in favor of the Big Bang.
And one of the most compelling pieces of evidence was the discovery of cosmic microwave background radiation.
Right. Absolutely. It's like the faint echo of the Big Bang.
Oh, wow.
A whisper from the early universe that pervades all of space. This discovery pretty much sealed the deal for the Big Bang model.
It's like finding a fossil from the very dawn of time. But, it's interesting how Hawking doesn't just present the facts.
Yeah.
He also takes us behind the scenes, showing us the debates, the challenges, the evolution of scientific thought.
That's what makes his writing so compelling. He makes you feel like you're part of the scientific process, grappling with these big questions alongside him. And speaking of big questions,
Okay.
A Brief History of Time dives into one of the most enigmatic phenomena in the universe. Black holes.
Black holes, they're like the ultimate cosmic vacuum cleaners, sucking up anything that gets too close.
Yeah.
I remember being fascinated by them as a kid, but the science behind them is pretty intense.
It is, but Hawking explains it with such clarity and elegance. He starts with the life cycle of stars, how they're born from collapsing clouds of gas and dust, how they spend billions of years fusing hydrogen into helium, releasing the energy that makes them shine.
And eventually they run out of fuel, right?
Exactly. And what happens next depends on the star's mass. For smaller stars, like our sun, they eventually puff up into red giants and then shrink down to white dwarfs, slowly cooling over billions of years.
But for massive stars, things get a lot more dramatic, don't they?
Oh, absolutely. When a massive star exhausts, its fuel gravity takes over and the core collapses in on itself with incredible force. This collapse can trigger a supernova explosion, one of the most energetic events in the universe.
So a supernova is basically a dying star's swan song.
In a way, yes, but it's a swan song that can outshine an entire galaxy, and for the most massive stars, the core collapse doesn't stop at a supernova. It keeps going, compressing the core until it becomes infinitely dense.
Infinitely dense? How is that even possible?
That's where the laws of physics as we know them start to break down.
Yeah.
This infinitely dense point is called a singularity, and it's surrounded by a region of space-time warped beyond recognition.
And that's the black hole, right? Where gravity is so strong that nothing, not even light, can escape.
Precisely. Hawking walks us through the mind-boggling implications of black holes, time dilation, spaghettification. the potential for singularities to exist at the hearts of galaxies.
Spaghettification. I think I'd rather not experience that firsthand. But seriously, black holes are both terrifying and fascinating.
Absolutely. They challenge our understanding of the universe, pushing us to the very limits of what we know. And just when you think you've got a handle on black holes, Hawking throws us another curveball: Hawking radiation.
Wait, black holes emit something? I thought nothing could escape them. How is that even possible?
Well, that's where the weirdness of quantum mechanics comes in. Even in the vacuum of space, there are these tiny fluctuations of energy where virtual particle pairs pop in and out of existence.
Virtual particles, so they're not real particles.
They're real in the sense that they have measurable effects, but they exist for incredibly short periods. Now imagine a virtual particle pair popping into existence near the event horizon of a black hole.
The event horizon. That's the point of no return, right?
Exactly. So one of these virtual particles might fall into the black hole while the other escapes. The escaping particle carries away some energy, and that energy has to come from somewhere.
So the black hole is essentially losing energy.
Precisely. It's like the black hole is slowly evaporating, emitting this faint radiation over vast stretches of time.
So black holes aren't completely black after all.
Well, technically, the radiation isn't coming from inside the black hole, but from the region just outside the event horizon. But the point is that black holes aren't these eternally static objects. They evolve, they radiate, they have a lifespan.
That's amazing. And it completely changes our understanding of these enigmatic objects.
Yeah.
Hawking's insight into black holes is truly revolutionary. He didn't just explain them, he fundamentally changed how we think about them.
He had a knack for seeing connections that others missed, and that's what makes A Brief History of Time such a landmark achievement. It's not just a summary of what we know, but a glimpse into the mind of a true visionary, pushing the boundaries of human understanding.
Welcome back to our deep dive into Stephen Hawking's A Brief History of Time. We've covered so much ground already.
We have.
From expanding universes to the mind-boggling physics of black holes. But the journey doesn't end there, does it?
Not at all. A Brief History of Time isn't just about the science, it's also about the philosophical questions that these discoveries raise. Hawking delves into some really deep stuff.
He does.
Like the arrow of time,
Right.
the possibility of time travel, and even the role of God in the universe.
That's what I love about this book. It's not afraid to tackle the big questions, the ones that have puzzled humanity for centuries. And Hawking approaches these questions with a blend of scientific rigor and a sense of wonder that's truly inspiring.
He does. So let's start with the arrow of time.
Okay.
Why does time seem to flow in one direction?
Right.
Why do we remember the past but not the future?
It seems so obvious, right? Time moves forward, but the laws of physics themselves don't have a preferred direction. They work just as well in reverse. So why do we experience this clear arrow of time?
It's a profound question. Hawking explores several different arrows of time, including the thermodynamic arrow,
Okay.
the psychological arrow, and the cosmological arrow.
I remember being fascinated by the thermodynamic arrow.
Yeah.
It's all about entropy, the idea that disorder tends to increase over time.
Exactly. It's why a broken egg doesn't spontaneously reassemble itself.
Right.
Why heat flows from hot to cold, why the universe seems to be moving from a state of order to disorder.
And the psychological arrow is our subjective experience of time, right? The feeling that time is flowing from past to future.
That's right. We remember the past, but we don't have memories of the future. And Hawking suggests that this psychological arrow might be connected to the thermodynamic arrow. Our brains are physical systems, and they operate in a way that's consistent with increasing entropy.
So our memories are like little pockets of order in an increasingly disordered universe.
In a way, yes. And then there's the cosmological arrow, which is tied to the expansion of the universe. As the universe expands, it becomes more disordered, so the direction of time might be linked to the direction of cosmic expansion.
It's like the universe is a giant clock, and its expansion is what sets the ticking of time. But even with these explanations, the arrow of time remains a bit of a mystery, doesn't it?
It does. It's one of those fundamental questions that keeps scientists and philosophers up at night. And then, of course, there's the tantalizing possibility of time travel. I mean, who hasn't dreamed of hopping in a time machine and visiting different eras?
I know I have. But is time travel even scientifically plausible?
It's definitely more than just science fiction. Hawking explores some intriguing possibilities, like wormholes.
Wormholes, those are like theoretical tunnels through space-time.
Exactly, and they could potentially connect distant points in space and time. The problem is that creating a wormhole that's stable enough for travel would require some exotic physics, like negative energy density.
Negative energy, isn't that something out of Star Trek?
It might sound like science fiction, but there's some evidence that negative energy might actually exist. The Casimir effect, for example,
Oh, wow.
is a quantum phenomenon where two metal pleats placed close together in a vacuum experience an attractive force. This force is thought to arise from negative energy fluctuations in the vacuum.
So it's not completely out of the realm of possibility that we could one day manipulate space-time to create wormholes.
It's highly speculative, but not entirely ruled out by the laws of physics. But even if wormholes are possible,
Right.
there are still paradoxes to consider.
Yeah.
What if you went back in time and accidentally prevented your own birth?
That's the classic grandfather paradox. It makes my head spin just thinking about it.
Hawking discusses various resolutions to these paradoxes, including the chronology protection conjecture, which suggests that the laws of physics might prevent time travel paradoxes from occurring.
So the universe might have a built-in safeguard against messing with the timeline.
It's possible. Another idea is that time travel might lead to the creation of parallel universes. So if you did go back and change the past, you'd create a new branch of reality while the original timeline remains intact.
Wow, that's a mind-blowing concept.
Yeah.
But I think what fascinates me the most about A Brief History of Time is Hawking's discussion of the role of God in the universe. It's a question that's been debated for millennia, and Hawking's perspective is incredibly thought-provoking.
He approaches this question with his signature blend of intellectual honesty and humility. He even quotes Einstein,
Yeah.
asking, how much choice did God have in constructing the universe?
And his answer is really interesting. He suggests that if the no-boundary proposal, the idea that the universe is finite but unbounded, is correct, then God might not have had any choice at all.
That's right. The laws of physics as they are might necessitate the existence of the universe. The Big Bang, the expansion, the formation of galaxies and stars, it might all be a consequence of those fundamental laws.
So it's not that God created the universe according to some grand design, but rather that the universe itself, with all its complexities and mysteries, is an expression of those laws.
It's a perspective that challenges our traditional notions of a creator deity, but it also highlights the incredible power and beauty of those fundamental laws.
It's a humbling thought, isn't it, to realize that we are part of this vast, intricate, self-contained system governed by laws that we are only beginning to understand?
It is, and that's what makes Stephen Hawking's work so inspiring. He dedicated his life to unraveling those laws, to pushing the boundaries of human knowledge, and in A Brief History of Time, he invites us all to join him on that journey of discovery.
It's been an incredible journey exploring the mind of Stephen Hawking through this book.
It has.
This book has opened my eyes to the wonders of the universe and the incredible power of the human mind to understand it. Stephen Hawking was a true visionary.
He was.
And his legacy will continue to inspire generations to come.
Absolutely. And if you want to learn more about the amazing things we talked about today, be sure to pick up A Brief History of Time.
Yes, and be sure to check out our other deep dives where we explore a wide range of fascinating topics. And don't forget to subscribe to our channel so you don't miss out on future episodes. Thanks for joining us.